Welcome, Mindsetters, to this Learn Extra Live session on a Saturday. Make sure you guys have your pens and pads out because we've got a full packed session just for you guys. By the way, so John, what are we going to be doing today?
Well, guys, it's paper 2.
All right, awesome.
Lots of chemistry. We did physics last week, and I know there are a lot of you that are still going to be writing paper 2 during this coming week. So get out your questions. Now, what are we going to do today? We're going to start with one of those previous exam question papers. We were all the way back to 2008, and we're going to be going through as many of those questions, different sections of the paper. We don't want to just get stuck on one topic because that's a bit boring.
No, definitely.
But at the same time, we're going to just be going over the key things you need to know in each of those sections.
All right, awesome.
So, but guys, if you've got problems, you've got questions, you want a further explanation, let us know on the page, phone us on the help desk number, and we'll get back to you. We'll try and answer all of those.
All right, so while John makes his way across there, I'm going to tell these guys what they need to do. Guys, make sure you get on the page. You know the link, www.facebook.com/learnextra. Get chatting to me, guys. If you're lost anywhere, as John said, make sure you post it on the page so I can get those questions to him so he can help you out. And guys, I am giving out these awesome winter packs. So make sure you call in on 0861 058 262. The first 5 callers to call in with the great question, you get to get one of these packs. But guys, make sure you keep chatting on the page though, so we can get those questions to John so he can help you out. And by the way, happy Youth Day, and I'm going to hand over to John now. John, take it away.
Thanks, Ty. Great to be with you, and let's get going. Now, remember in paper 2, a lot of questions that I've seen come up on the page already. What's in paper 2? You need to recognize we've got organic chemistry, and then we've got effect of reactions, chemical change. So we need to do rates of reaction, chemical equilibrium. And then there's electrochemistry, redox. And the last section is on chemical systems, which is batteries, fertilizers, chlor-alkali, all those industrial processes. We're going to jump in with one of the easy questions and the easy sections that it requires a little bit of book work and a quick summary of that. But I thought as a warm-up, let's get going with rates of reaction. So have a look here. We're going to be posting the question on the page as well. This is taken from the November 2008 exam paper, and I'll discuss what the trend has been in other exam papers so that you can get an idea of what's happening and make sure that you're absolutely ready and prepared for your coming June exam. Okay, so let's go to it. Rates of reaction. And remember what rates is about. What is a rate? A rate is what happens. It's the measurement of how much product is produced in a certain time. So what do we go to? In this question here, it says 8.1, the collision theory can be used to explain how different factors affect the rate of reaction. So we want to, of the chemical reaction, name 2 conditions. Now when they put it in bold and capital, we need to make sure that we do give 2 that determine whether a collision between 2 molecules, A and B, will lead to a chemical reaction. So this is an interpretation of your theory, collision theory. Remember, we have reactant molecules. Those are the things that we have at the start. So collision, molecule A and molecule B. What turns them into a product molecule, an AB or an A2B or something like that? Well, first of all, the first thing we're going to need to say here is they need to have enough energy. They need to have enough energy. Right? The second thing that you need to recognize and you need to be able to say is they could have too much energy. They mustn't have too much energy, because think about it, we've got like particles rushing towards each other. They could bang into each other and spin off. We don't want that to happen. We don't want to have them too little energy, because then the electron clouds will repel each other. They need to just have enough energy, more than the activation energy, but not too much energy. The second thing that's really important from collision theory is they must orientate themselves. They must have the correct orientation. So if the unpaired electron is sitting, for example, on one molecule over here, or that's the bonding position, and the other one is on the back of it, and they bump into each other, no reaction. So they must have correct orientation. Correct spatial, that means just in space, spatial orientation. Okay, so these are critical ideas in terms of collision theory. We need to make sure that they have that they're ready for bonding as well, so that they're likely to form product molecules. But those are two big conditions, and we've gone through that first question. Now let's go on to the next one. It tells us that we have a particular reaction, and the reaction is given here. I just want to change the color of the pen. We're told the reaction between nitrogen dioxide and carbon monoxide is represented by the equation below. There's your nitrogen dioxide, there's your carbon monoxide, and we're getting nitrogen 2 oxide and carbon dioxide. Remember the information here, delta H is minus 226 kilojoules. That's telling you about whether it's endothermic or exothermic. We need to just go over those terms. Exothermic means that more energy is given out in the reaction, and delta H is negative. Endothermic, delta H will be positive, and it's saying more energy is taken in, less is given out. Okay, so revise those terms and make sure you've got them sorted out. We'll come to them again. It tells us that the activation energy is 132 kilojoules. Now, it says sketch a potential energy graph against the reaction coordinate for this reaction. Label the reactions and indicate the delta H and the activation energy on the graph. So let's go to it over here. I'm going to pick a system of axes, and we do that, and let's draw in. This is bookwork, and you should really know this stuff quite well. Revise it, get your notes sorted out so that you've got it perfectly sorted out here. Now, remember what we've said. We've interpreted the data. We've said over here, this is a negative, so it's exothermic. It's telling us that the energy, potential energy of the products is less at least than the energy of the reactants. So there's the products. The products is down here. And the reactants are up here. So this is potential energy. And these are the reactants. And the products are down there. So now, what else do we know is going to happen in terms of the reaction coordinate? So we just say reaction coordinate, because it told us to label the axes, and its potential energy, you could write it in words in kilojoules, and we want to be able to show it on the graph, so we need to make sure we label it carefully and label it accurately. So what's the next thing? We've got 132 as the activation energy and minus 226 as the delta H. So delta H, enthalpy, the energy of reaction, heat of reaction, the amount of the difference between the product and the reactants. We've got them in the right position. So what we're going to say is the difference between these two. This is an exothermic reaction, and the difference between those two is your delta H value. So this value is going to be 200 minus 226 kilojoules. And I'll put a minus in there so that we know it's exothermic. Remember, you need to label that, and then we need to complete the drawing. So what happens? The next part, we know we need to put some energy in to get the reaction going, and energy is given out. Now, let me just neaten that drawing up there a little bit. fill that in and get it in a straight line, and we've got it like that. So where's the activation energy now? Remember, activation energy is the energy that you start with until it forms a in-between situation up here. This is called your intermediate point. That's the most energy that's taken in. It's known as the coordinate. It's the reaction, it's a complex. In other words, what's happened here is the two molecules have joined together, and the new bonds and the old bonds haven't quite broken. It's an intermediate stage. It's the activation complex that is formed at that point. Now, when you get this complex molecule of these two things kind of stuck together, they haven't quite bonded yet, and they haven't quite broken all the existing bonds, they then can either break apart to form reactant molecules, or form new bonds to make product molecules. So we call this the activation complex. Activation complex, and that's your activation energy. Now, why is activation energy important? Well, here's the thing. Ty, I don't know if you know that, I mean, you've got some books sitting on your desk at the moment, and those are mainly made out of carbon. Okay, and there's oxygen in the room. So guys, we know that oxygen and carbon, paper burns. So why aren't the books combusting at the moment?
I'm pretty sure it's because there's not enough volatile energy to cause them to.
Okay, correct. There's not enough activation energy. We'd need a little spark. And hopefully we don't have too many sparks flying around in the studio today. But if we had a little spark provided by a lighter or a match, that would give enough energy to get some molecules excited enough to start reacting with each other. So the carbon molecules in the paper would react with the oxygen molecules in the air, and the next thing, there'd be an exothermic reaction, and we would see flame. Flame is an emission of light and heat. And so that's why we say this is an exothermic reaction. In this particular case, you might not see flame and heat, but you'd be able to measure a change in temperature. Okay, so I think that we've more or less answered the question. Once you've put things in, make sure that you reread your question. So after you've gone through the question and you think you've finished, just read through and make sure you've got everything sorted. So it said sketch a potential energy, potential energy I've written as EP, versus reaction coordinate, I've labeled that for this reaction. Label the axes and indicate the following on your graph, delta H and EA. So I've shown the delta H just to make sure that people are perfectly happy with me. I'm going to put in another line just to show where the EA, the delta H comes to. So it's the difference between the product and the reactant. So I could move this arrow over here because it's from that line to that line, and my line was just a little bit short, so let me make sure that you've got that. You need to work accurately. It's between these 2 points here. Make sure that you've got that very clearly put in, and make sure that we've got it as minus 226 kilojoules. Ty, any questions on the page at the moment?
Not as of yet. Right now, I'm just pretty much waiting for the page to reload.
Okay, that's fine. Let's go on to the next part of this question. Well, we have done the rates of reaction question. I think we could go to a short break if there's nobody asking. One further thing, guys, just before we do go to that break, what are the type of questions that are being asked in more recent exam papers on rates of reaction? And the thing that you need to remember is, apart from these, look there, I missed the question. I knew there was another one. Here we go. Use a broken line on your graph to show the effect of a catalyst. And that was just the point that I was coming to. So the effect of a catalyst on the potential energy as the reaction proceeds. The point I was going to make is, guys, you've got to know the 5 or the 4 factors that affect a rate of reaction. It's the concentration of reactants, it's the temperature, it's the surface area, and it's the effect of a catalyst. So let's deal with the effect of the catalyst. What is a catalyst, and what does a catalyst do? A catalyst is a substance, it's a chemical substance that we introduce into a reaction, and it takes part in the reaction, but it isn't used up. So we start with a certain number of moles or mass of catalytic substance. At the end of the reaction, we would have the same mass, the same molecules, the same number of moles. It's not used up. It can be changed in the reaction. It helps to make the reaction happen faster. It helps speed up the rate of reaction without being changed itself, without being used up itself. Okay? So it effectively lowers the activation energy. So instead of having an activation energy of 132 here, if I were to put a catalytic reaction in this example, I'm going to use that color, then the catalyst would go up to there, it would end in the same place, and this line here is with the catalyst. So you can see that it says draw a broken line. I've just used a different color. It's just easier to do it smoothly on the board. Hope you can see, follow the instruction. That should be a dotted line to indicate that that's the catalytic. Notice that the energy, the activation energy, this is the activation energy now, and it's going to be less than the original 132. Okay, remember that when they're asking these questions now, they often ask about investigative questions. They set it up and say to you, describe what is an investigation, what's the investigative question, what's the hypothesis, what variables would you control, and ask questions like that. That's the way they've been tending to examine this section in the last couple of years. Okay, Ty, over to you.
All right, so mindsetters, I'm seeing and I'm loving what you guys are doing on the page. Keep posting. But guys, we need questions. Make sure you post questions. And guys, don't forget to call in on 0861 058 262. Make sure, because you could stand a chance to get one of these books, this pack sent to you. But guys, again, do not go anywhere. Make sure you stay tuned, and we'll see you after this break. Welcome back, Mindsetters, on this lovely Saturday morning. Guys, again, I stress, enjoy your youth day, but make sure you also understand it and what it actually means. Ask your parents. I know it seems like your parents weren't youth, but they were at some point. So make sure you ask them and find out more about today. And guys, again, call in on 0861 058 262, and you could get one of these packs sent to you. So guys, also keep posting on the page. If you lost any, if you need help, make sure you get those questions on the page so I can get them to John. But for now, I'm going to hand back to John. John, take it away.
Thanks, Ty. Yeah, guys, Youth Day is really important. You know what? It's all about education. That's where it started. And we're here today because of the courage and the bravery of your parents and many of the young people back there in 1976. So let's get going and make sure that we don't give up because of what was done for the struggle in those days. It's about you getting involved in your struggle to improve your fate in education as well. So let's get going with these questions. We're looking at the 2008 exam paper, and we're going on to our next question. We've done some stuff on rates of reaction. We're going on to redox, and the tie between redox and electrochemistry is really important. So let's make sure we've got these basics in place. Redox, remember what redox is. Redox is broken down into two parts. It's reduction and oxidation. And we're looking at reactions in which these two half reactions take place. That means that there is a transfer of electrons. You need to understand it. You need to be able to identify what is oxidation, what is reduction? How are you going to remember it? Well, there are lots of little ways of doing it. The way I remember it, the way I was taught, and the way that I still remember it is the following. And I just want to make a note of it. That I say reduction is a gain. So I write the word R-I-G, reduction, R, I for is, gain, G. Spells the word rig RIG. Oxidation is a loss, OIL. So you've got oil, rig. Oil, oxidation is loss, reduction is gain. If you remember that, you won't have a problem. You'll always get it right. But we've also got an interesting thing. We've got a table that's given in every exam. Now, I've just got a big one blown up here because I need big writing to read, going a bit blind, you know, or short-sighted, at least far-sighted. So I've got the big table here to make sure that we refer to it. This question actually refers to it. It's table 4 and 4A and 4B. We'll be having a look at that just now. The table is also very useful in determining which things are undergoing, more likely to undergo oxidation, and which ones are more likely to undergo reduction. Make sure you're familiar with the table, because the table is very useful. I use table 4B, and I remember the reducing agents, the things that undergo oxidation, are on the right-hand side. And we'll come to that shortly. Right, let's have a look at the question. It says, rusting is an unwanted reaction happening around us. It's an unwanted redox reaction. Iron rusts when exposed to oxygen and moisture, and the unbalanced ionic equation for the one reaction that occurs during rusting is represented below. So what we've got here is iron as a solid, oxygen as a gas, and some water, and then we're producing iron 2+ ions in solution. That should really be a superscript, and hydroxide ions as the ionic reaction. Now, it then says, use the table of standard reduction potentials. That's the one on the data sheet, the big one at the back of the data sheet. Make sure you're familiar with the one that use 1. Don't change between 4A and 4B. The one I prefer is 4B, because I look to myself and I say, where is lithium? Oh, sorry, where is potassium and sodium and lithium? And they're at the top on the right. Where is fluorine? In fact, fluorine is the one that you know always. It's the strongest oxidizing agent. It's bottom left. Okay? So F2 and lithium at the top, F2 at the bottom. Bottom left, top right. And you've got then, you know where you're at. So we now need to write down the oxidation half reaction. Now, guys, oxidation is a loss of electrons. The thing that undergoes oxidation is known as the reducing agent. Reducing agent always donates electrons, so it's losing electrons. So it is the thing that undergoes oxidation. It makes reduction happen to the other stuff. So if I was a reducing agent, I would want to donate something to Ty, who might be undergoing reduction. He's going to gain the electrons. I'm losing, he's gaining. You got it? Hope so. So we want to get the strongest reducing agents. Now, think about it now. In all the chemistry you've done, which elements are most likely to lose electrons? What's the metals? The non-metals tend to gain electrons. So we're going to look amongst the metals. We've got here a metal, iron, oxygen and water, and we're producing hydroxide ions. And we're producing iron 2+ ions. So even without looking at the table, just from my knowledge of chemistry, I'm going to start to identify what is the most likely reducing agent. Which is the one that's most likely to undergo oxidation? I think it could be the metal. And so we recognize as well, without even looking at the table, we can do this, and we can say to ourselves, we know from grade 11 work that the oxidation number of iron is 0. As an element, oxidation number is 0. Okay? It's neutral. Oxidation number of iron 2+ is +2. So what's happened to go from 0 to +2? Well, it's lost electrons. What is oxidation? Loss of electrons. So here we go. Without even looking at the table, you can confirm it by looking at the table, but I'm going to recognize from this that I've got iron to start with, and I've ended up with iron 2+ in aqueous solution. How did I get there? Well, I lost some electrons, and I've got iron 2 plus 2 electrons. And there's my oxidation half reaction. Now, if you go to the table, and table 4b, I know you won't be able to see it. What you're going to do is you're going to go to the right-hand side. On the right-hand side, you go down the page until you see the one, either oxygen or iron. From the top, I get to iron. First, above oxygen. And then what I'm going to do is I'm going to read from right to left, and I write it from right on this side. It normally reads the other way around, but I turn it around, and I start with the iron on the right-hand side, and I'd be able to write it down as iron goes to iron 2 plus in aqueous plus 2 electrons. Easy one to get going. Let's move on to the next one. Write down the name of the substance that is reduced. Okay, so let's go back to the equation, and we recognize here that we've got oxygen starting at 0. So I just want to change the numbers, because oxygen as a substance is an element. It's a neutral molecule. It has an oxidation number of 0. And it's forming oxygen over here. The only other thing that I can see here is oxygen, and it is at -2. So what's happened to the oxygen? I hope you can see, if I start at 0 and I get to -2, I've become more negative. What does that mean? Become more negative? I've gained electrons. Got it? If you gain electrons, what was a gain of electrons? Reduction. Reduction is a gain, oxidation is a loss. Now, don't get confused. Because it's becoming more negative, you might think, well, that's losing. No, becoming more negative is gaining a negative thing. It's gaining the electrons. So it's undergoing reduction. So what substance is undergoing reduction? We are asked to write the name. Now, guys, the examiners are sometimes a little bit fussy about this. They've said name. Please don't write down the formula. What was the stuff that undergoes reduction from the equation? We can see it's O2. What is O2? It's oxygen. So write down oxygen. Don't write down anything else. Don't write O2 or O, oxygen, and you could even write down gas if you really wanted to, because it said O2 with a G. So oxygen gas is the thing that is undergoing reduction. It's being reduced. Right. Next. Perform a calculation to verify, that means to explain, to confirm that this reaction is spontaneous. We know it's spontaneous. It's happening around us. We know that if we leave some iron nails with some water on the surface out in the air, it's going to turn that brownish color. Iron rusts in air. Happens. We don't have to put a fire underneath it. We don't have to increase the temperature. We just have to leave it out in the air, and over time it will rust. So, but how can we confirm it? Now, this is where the table of half reactions comes in, and it's really useful for, it's really useful for us. What we need to do is we need to confirm the two half reactions, and we use the table to read off data from those half reactions. So I'm going to go back to my table, and I'm going to write down my half reactions. So let's do that. I'm going to say iron goes to iron 2 plus 2 electrons, and I'm going to say oxygen. Now on the table I need to look up oxygen on the left hand side, and we'll find it as we look it down. We recognize that we want the one that goes to OH on the other side, OH minus. So oxygen plus some water, H2O, plus 4 electrons, there was 2 of those, gives us 4 H minus. Let me just make sure that you can see that. I want to just rewrite it, so write it a little bit bigger. I'm going to erase that one, but I want to just get it a bit bigger, because I squashed it up. 4OH minus. Good. Okay, so there are my two equations. This one I've already, the top one, first one, I've changed around. Second one is the one that was with the oxygen. I've just read those off the table. This is undergoing oxidation, and this one is undergoing reduction. And you can see it. Look, it's gaining 4 electrons. So we know it's gaining electrons is reduction. Guys, what you need to do next is you need to go and look at the table and fill in the values here that are known as the E0 values. These values come from the electrochemical cells. We fill those values in and then do the calculation. I think we need to go to a quick break, and while you go to the break, I'm going to pick up the values and we'll set up the calculation. And back to you, Ty.
All right, so mindsetters, as I've been saying earlier, make sure you get posting on the page. Keep posting, because guys, the more frequent you are on the page, the higher your chances of getting one of these sent to you. But guys, also, I stress, make sure you keep chatting to each other. If you see a mindsetter and they're struggling, make sure you at least do your best to help them out. But you know what, guys, for me, I'm going to say, see you after this quick break. Welcome back, Mindsetters, to this Learn Extra session for grade 12 science. Guys, keep posting on the page. I'm loving what I'm seeing. I'm seeing you guys are definitely loving the show. So guys, I stress again, make sure you get on the page. By the way, John, we had a question from Tsepo. He says, Ty, I hear there are 7 electrolytic cells. Are we supposed to learn them all?
Okay, Ty, thanks. That's a really good question. Now, when we deal with electrochemistry, I haven't counted them all up. So electrolytic is about electrolysis. You certainly need to know about the production of chlorine. And there are 3 cells there. There's the membrane cell, there's the mercury cell, and there's the graphite cell. So you need to know those 3. You need to know the dangers and the environmental impacts of those. So that's one group of 3 that I'm aware of. You also need to know the electrolytic cell that's used for the recovery of aluminium. So that's another one. So I make it 4. I'm not sure about the 7. I suppose you could say that if you're looking at refining of metals like gold and copper, that's another type of one where they purify the gold and copper, where they do electroplating. That would be another one. But they're all quite similar. But they could change the metals, so don't learn them as particular ones. You could get in the exam where you've studied the gold cell, you might get one that's doing refining of nickel, but the principle is the same. I hope that helps it. I only count 6 though in total. So yeah.
All right. So then we also had another one from Nokulo. Sorry, I'm trying my best. She says, hi Ty, can you please ask John to explain how increasing concentration changes the rate of reaction time graph and the concentration time graph?
Okay, we will come back to that one in a little while. I just want to finish off this calculation. And then we'll get straight into that. Before we do some chemical equilibrium. Now, guys, I deliberately have left chemical equilibrium because I know that we want to spend a good time on that. But I don't want to just do KC calculations all the time. So tune in, make sure that you're with it, because this is a section that I know that a lot of you struggle with, but we want to make sure that from today on, you're going to ace KC questions. So let me answer this, then I'll answer that question, and we'll get on to KC in a minute. So here we go. Remember what we were saying? We had to do a calculation to verify that this was a spontaneous reaction. So what I've done is I went and looked on the values on the table, and I found that the iron-iron 2 reaction has a value of negative 0.44 volts. It's important that you write the negative in. Don't lose the negative. It's there. It's if you were using a half cell with iron and iron 2+, then connected to the hydrogen half cell, the standard hydrogen half cell, you would get a voltage reading on the voltmeter of minus 0.44. That would be because the iron is the anode. It is the source of electrons. It's where you're going to get oxidation. Anode oxidation, the vowels go together. Okay, in this case, we find that for oxygen, the value is plus 0.4. That's telling us that compared to the hydrogen half cell, that this is going to be the cathode. So now when we connect these two together, we know that it is like a cell reaction. It's like the electrochemical cell. So we're taking something from electrochemistry to see if it's spontaneous. Remember, the galvanic cell is the spontaneous one. If you connect an iron 2+, an oxygen and water cell together, connect those two together, it will be a galvanic cell. You don't need to push energy in. And the calculation to confirm that is you do this calculation. Equation on the data sheet is given as, the formula on the data sheet is the E naught of the cell. The reading on the voltmeter is the E naught of the anode minus the E naught of the cathode. It also does it as E naught reducing agent minus E naught oxidizing agent. It also does it as E naught oxidizing minus E naught reducing. So we can make sure that we've got it right. I prefer the anode minus cathode, and I remember that's where oxidation, that's where reduction takes place. Now I sub in the values. And the first value, the anode value, was minus 0.44. You know what? It's the other way around. I've made a mistake. It's the cathode minus the anode. So I wrote down the formula wrong. Never do that. Remember it from the right check on the data sheet. It's cathode minus anode. And here we go. We're going to say cathode value 0.40 minus. Now this is where a lot of you sometimes make a mistake, because we've got to put a bracket around this value. And we're going to say minus 0.44. Now, remember, when you've got a minus, it's always a thing to be careful about. Because the minus times a minus gives you a plus, and the value that we're going to get is going to be 0.84. Now, in this case, it's volts, and notice it is a positive value. Very important that you recognize that this is positive. If it's a positive value, you've shown by calculation that it's spontaneous. If it turned out to be a negative value, then it would be non-spontaneous. Then it would be not a galvanic cell, but an electrolytic cell, the ones that we mentioned earlier. Okay, so, right, let's go on to that question. Just repeat it again for us and for the viewers that might have missed it, the one about the reaction rates.
She wanted to find out how concentration affects the reaction rates and the reaction time graph.
Okay, so I'm going to just pick a set of axes here, and I'm just drawing them up quickly. So just give me a second, and we'll take a particular example. Do this one. We're going to say we have hydrochloric acid and zinc. Okay, and hydrochloric acid and zinc produces for us hydrogen and zinc chloride. Now, if we were to balance the reaction, we put a 2 in front of there, and now we've got a balanced reaction. Over here on the reaction on the axes, I'm going to say that this is the volume of hydrogen produced, the volume of hydrogen in centimeters cubed, and this is time. Now, I haven't got the exact readings, but it's usually measured in minutes, can be seconds, but let's put it like that. So what do we know when we put some zinc and hydrochloric acid together? We get these bubbles of hydrogen gas, and we can measure the volume of hydrogen produced in a few minutes. So what does the graph look like? Well, in this case, the graph tends to be a kind of straight line, and then it starts to curve, and it does something like that. Now, they sometimes ask you about interpreting this graph, and they say, well, what does this tell you? At this point, we recognize that we've got more or less a straight line between those 2 points, between the top point over here and over here. That's more or less a straight line. The gradient is constant, and we've got a positive gradient, and we can say that the change in volume over the change in time is equal to the rate. Okay? The rate of reaction. Now, we'd have to say that there was a certain concentration of this one. Let's call this 1 molar. What is that's saying 1 mole per decimeter cubed, 1 molar hydrochloric acid. And that's the green line. What are we saying over here? We're saying that there's no more hydrogen produced. This says the reaction is at its end. It's ended. There's no new product. No new product. So it's over. Once it goes flat, it's finished. You with me? I hope so. Now, the question is, what would happen if we used a more concentrated acid? The same volume of the acid, but it was more concentrated. So instead of 1 mole per decimeter cubed, I'm going to use a different line now. Let's say I used a 2 mole per decimeter cubed sample of acid. So I'm going to use 2 mole per decimeter cubed. What this is saying, guys, is that this was time t. It took all of time t. Let's say that was 10 minutes to produce. I've doubled the concentration. I've increased the number of molecules that are present. They can move around. More effective collisions can take place. Okay? Got the same volume, but I've got twice as many moles of substance. Well, that tells me that they're going to react faster. And in this case, what we're going to see is that because we've got twice the concentration, remember, concentration is equal to number of moles divided by volume. And if we've got the same volume, the number of moles is equal to concentration times, that's right, the number of moles times volume. If we keep the volume the same and we double the concentration, we're doubling the number of moles. We're going to get more moles. So there are 2 aspects to this graph that are really important to take note of. We've got more stuff present, and we've got, so the chances of them colliding are going to be greater. So the end product, if we've got an excess, it's important, if we've got lots of this around, if that's in excess, then what we're going to find is our graph is going to look like this. It's going to be a steeper line, and it's going to be twice as high. So it's going to be up somewhere over there. I haven't even got space to do it. But the line will be twice as steep. So if the gradient of this was, say, 1, the gradient of this would be 2. It's increased in its speed. It's saying it's going to produce more stuff in half the time. So it would produce the same amount of stuff in half the time. Generally, we don't ask specifics about it. You're just asked to draw sketches. So if we had half the concentration, well, the line here would be lower down. The gradient would be somewhere there. Okay. Often what they do is they say to you, you've got this, the one substance isn't in excess. So you've only got a certain number of reactions. The products then will be the same volume, and they can show you graphs like this. This would be less concentrated. This one is higher concentration. And concentration, I'm just writing as CO and C. Okay, I think we can just brief the chemical equilibrium question, and we'll make sure. Are there any other questions, follow-up questions to this one?
I think so. There was one from Bradley. He just wanted to find out, why is the reaction in galvanic cells always spontaneous?
Okay, remember, guys, Galvanic cells. Those are the ones where you're using chemical energy to make electricity. So what do? We get a chemical reaction and we get energy out. That's the spontaneous. That's what galvanic cells do. Even your batteries at home, they are producing energy. They're producers of energy. So that's why they're spontaneous. An electrolytic cell is the opposite way around. We're going to need energy to make a chemical reaction. Okay? Now, under normal conditions, you're not going to find a less reactive substance reacting with a more reactive substance to give you a product. The more reactive substance always reacts with the less reactive substance. In electrolytic cells, you need to provide the energy to make the chemical reaction happen. Hope that answers it.
I think so.
Okay, let's just quickly flick to chemical equilibrium. I think it is on this page. And yeah, let's have a quick read through the chemical equilibrium question. So it says, the following equation represents a reversible reaction. And I just want to fill in some stuff here. The reversible reaction, double arrow, in a closed system at 470 degrees in a closed container. We're told that it's the ammonia production of ammonia. Nitrogen plus hydrogen gives us 2 lots of ammonia, and we're told that the delta H is less than 0. We're saying that's exothermic. Guys, give you a hint. Learn the Haber process reaction. This reaction often comes up in chemical equilibrium. So a change was then made, so it was at equilibrium, was made to the ammonia in the equilibrium mixture at T2. Okay? A graph showing the effect of this change is drawn below. The graph is not drawn to scale, but let's have a look at the graph. So we are dealing with a graph that deals with the amount of moles, and we are dealing with time. So there we go. And it's the gases versus time, the amount of gas versus time. So what can we read from this? I just want to get into it, have a look at it, and say to you, there's something's happened at T2. We know here we were in equilibrium, and here there's a change. So what's happening? Guys, you work it out. Tell Ty on the page. We'd like to highlight what you're saying. Have a careful look. The nitrogen is increasing. The ammonia goes straight up and then suddenly decreases. The hydrogen increases slowly. So which one, what factor is changing? Tell Ty on the page. We'd like to highlight the person that gives us the right answer, the first person, and we might even get in touch with you and send you a pack of winter school books. Let's go to a break, Ty.
All right. So mindset is, on that note, as John said, make sure you get on the page. Make sure you get chatting. So, guys, you can win a chance to get one of these sent to you. But for now, guys, we're going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. You guys went and did whatever you had to do. You went to the bathroom. You went and did whatever, so you don't have to scramble around or move or go anywhere. Make sure you have your tea, you have your blanket, you're nice and warm, and you guys are on the page and you're chatting to each other. Make sure you keep active on the page, and you could have one of these packs sent to you. But for now, guys, I'm actually going to hand over to John, who's going to continue with the session.
Thanks, Ty. Great to be with you. Remember, we're doing chemical equilibrium. November 2008, a great little question on chemical equilibrium. Now, before we went to the break, we were looking at the graph they gave you. And I want to just go over the graph before we actually get into the question. And we started to highlight some things on the graph. And we said, look, there's straight lines here. We're told from the diagram that at this point, we're in a state of equilibrium. And then something happens over here at T2, and I'm guessing they're going to ask us about that. They're saying the equilibrium was disturbed in some way, and then there's a change, and notice what happens. We get parallel lines here. So we haven't read through the actual questions, but I asked you to identify, what do you think is that change happening at T2? What's happened? What's happened? Here. tell us. Put it on the page. Post it now. And we'll see if we can get you a winter school pack. Meantime, let's get to the questions that were actually in the exam paper. The first thing that it asks us, it says to us, what is the meaning of the horizontal lines between T1 and T2? Let's have a quick look at it again. We highlighted them over here, the horizontal lines between T1 and T2. And let's have a quick look. There we go. And we've already written it. If you write down on your page in your exam paper what you think, even before you read the question, you know that you confirmed it, but I want to explain it. What this is saying is that the amount is not changing. It's not changing. There's no change between hydrogen, nitrogen, and ammonia. The number of moles is staying the same. So what do we know about that? We're saying there is no change in the moles of hydrogen, nitrogen, and ammonia. Now, we also know that there is no change in the volume. It's a closed system. So that means that the concentration is constant. And if the concentration is constant, that means at a macroscopic level, we're not seeing any shifts. We're not seeing any changes. But you know what? At a microscopic level, there is continual change. The products are forming reactants, and the reactants are forming products. They are in dynamic equilibrium. The rate of the forward reaction is equal to the rate of reverse reaction. And so it appears that the concentration is not changing. We say that because the concentration is constant, we say that we can recognize that this is a state of chemical equilibrium. So the system is in chemical equilibrium. We define chemical equilibrium as when the rate of the forward reaction is equal to the rate of the reverse reaction. Okay? Now, Ty, the question says, state the change that was made to the ammonia in the reaction mixture at T2. Has anyone posted an answer?
So far, what I've seen is Bradley has gotten the closest answer because he was using Le Chatelier's principle.
Yeah.
And
what did he say?
He said that in the equation, the volume is increased.
Okay, Bradley, we've got a little problem there. Let's have a look at the graph again. What we noticed, and I think that what you need to see is you've got only one thing that increases sharply. Only one thing.
Sorry, on correction, he actually reposted it. No, I meant on concentration has increased.
Ah, okay, Bradley, you got it right. In other words, what we're saying is, if we look at and we need to be careful here as well, because this graph is about the number of moles. So from the graph, we can say the number of moles of ammonia has increased. That means that the concentration increases. Okay? The volume stays the same. There's no change in volume. But this straight line up here is a giveaway. But don't get confused. The graph is about the number of moles, the amount of moles. So the correct answer that we need to say is we've increased the number of moles of ammonia. Right, which means, in effect, that the concentration, remember concentration is written in square brackets, and I'm just writing it in square brackets, the concentration increases. Okay, now, I think we're getting on to Bradley's next reference, because he referred to Le Chatelier. So what is this saying? Explain how the change mentioned in the question above affects the concentration of hydrogen and nitrogen as shown in the graph. Well, let's go back to the graph and have a look at it, even if we've forgotten and we're not sure. So notice from the graph what is happening to nitrogen, and there's nitrogen. What's happening? It increases. It's getting more. What happens to nitrogen? It increases. Now, notice that there's more hydrogen being formed and slightly less nitrogen being formed. What's happening to the ammonia? Look here. The ammonia is actually starting to, after increasing, it's starting to fall away. It starts to get less. So it jumps up, spikes up, and then it starts to fall away. Whereas the nitrogen and hydrogen increase slowly. Now, that we're going to have to explain. So I've said it in words, but what I would put it in writing, explain how the increase of that, what's going to happen. We're going to say here, reading from the graph, we can say that hydrogen and nitrogen both increase between T2 and that's 2 and T3. Okay. Now, what does that mean? Let's have a look at the equation so we can write it down and we can explain it a little bit further so we've got some understanding of exactly what's happened. And we're going to refer to Le Chatelier as we do this. We're going to say N2 plus H2 is in chemical equilibrium with NH3. And we know that's 2 of those and 3 of those. So what did we do? We created a stress. We put more of this. We increased this. What does Le Chatelier do? It says if you have a stress, like increasing the number of moles of one of the substances, it's going to try and reverse that stress. How does it do it? It's going to try and use it up. So you put more in, it tries to use the more up. So it's going to try and decrease it. And that's exactly, you've created the stress, where you increase that, and so it tries to use it up. How is it going to use it up? It's going to favor the reverse reaction. So it's going to no longer be in chemical equilibrium. We say the reverse reaction is favored. So this one speeds up, is favored. Okay? It speeds up. And what does the speeding up reverse reaction do? Well, we're suddenly going to get more of that and more of that. It's very interesting to notice that you can see the 3 over here and the 1 over here. And if you look at the graph, notice we showed that this was 3 times the increase. This was just 1 times the increase. Very small increase over there and quite a big increase over there. Whereas this was dropping by 2 times. It's in proportion to that balanced equation. Right. Now, the next question is the one that we're going to set up and we're going to take some time with, because I think this is the one that learners get into a panic the most. And Ty, if you look on the page, lots of people will be saying, I'm struggling with KC calculations. We're going to sort that out now. Let's have a look at this question. Okay, so look what it says. It says calculate the equilibrium constant, the Kc, at 420 degrees. But it gives us some information. It says we've got at the start 1,5 moles of N2 and 2 moles of H2 were injected into a 0,5 decimeter closed vessel and allowed to reach equilibrium. Okay? When equilibrium was reached, it was found that we had 1 mole of ammonia. Now, the next question is calculate the equilibrium constant and show all your calculations. Now, guys, when I do this calculation, I prefer to put it into a table. But the first thing that I want to do, and I want to stress to you, is you must make sure that you're working with all the values, all the information you're given in the same units. And I prefer to work with units of moles. So let's have a check with it. We're going to start, and in this case, we're going to say at the start, And another word for start is initial. And we're going to say initial H2 was 2 moles. And N2 was 1,5 moles. If they give you mass or they give you concentration, change it. Don't keep it in grams or anything else. Remember the formula to change from grams to moles, it's the mass divided by the molar mass. So if they give it to you in something other form, they could even give it to you in concentration, then change it to moles. The number of moles is equal to the concentration times the volume. Make sure that you don't make the mistake. You want everything in moles. Okay? We also know that the moles at the end, at equilibrium, were given as 1 mole. So ammonia is 1 mole. Be very careful. The next important information that we don't want to lose is the volume. So we write down the volume, and we must make sure that volume is in decimeters cubed. If they give it to you in centimeters cubed, convert it. Make sure that you've got the units all right. So write down your information. You don't even have to write this down. Just tick it off, highlight it, make sure you've got it. Okay? That's the first checking step. The next step, and this is where a lot of learners lose an unnecessary mark. You must write down the Kc expression. Now you can do it later on in the question, but I tell all my learners that they must write it down right at the start, because there's 1 mark allocated for it. And so you must write down the Kc expression for this reaction, not for some other reaction, not for some general thing. We know that we can say a Kc is the concentration of the products divided by the concentration of the reactants, and we can learn it like that and put A's and B's and all that sort of thing. That's not good enough. You're not going to get credit for it. So put it down in terms of this reaction. So what I like to do is I like to write down the equation or the Kc expression first, and I'm going to say I know my product is ammonia. And I know that in the balanced equation that was given, there were 2 lots of ammonia, so I'm writing it as squared. I'm then going to say hydrogen was the next substance, and I know that hydrogen H2 is cubed. I also know that my next substance was nitrogen. There was only 1 of those. So I can check it that that's the Kc expression for this reaction. Please make sure that you do check it, because the next step that you're going to write down on your piece of paper is to write the balanced equation. So you write down the Kc expression first of all. You might want to leave yourself some space if you are fussy, but it's not that difficult to rewrite it if we need it. You're going to get a mark here. You're going to get 1 mark for writing that down. Easy as anything. Then you write down the balanced equation. And we say it's in chemical equilibrium, and we write it down like that. Now, the next thing that we're going to do is we're going to draw up the Rice table. We're going to have the ratio, the initial concentration, the concentration at equilibrium, and the final thing. I'm going to draw that table up while you go to a short break. Ty?
All right, so mindset is on that note. Guys, make sure you keep posting on the page. I'm loving what I'm seeing. Guys, it's awesome. Always glad to have you guys on the page. But guys, make sure you do not go anywhere. If you need to go anywhere, you literally have this break to do it in. If you need to go to the bathroom, you need to get a snack, whatever you need to do, do it now. So when you get back, you can stay glued to your seats for this last session. But for now, we're going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. I hope you guys went and grabbed yourself some snacks, something warm, a blanket. I know I've been saying that a lot, but make sure you're warm, because winter is super cold. And guys, I don't want you to forget that today is June 16th, Youth Day. Enjoy it, treasure it, learn about it. Make sure you look it up. Ask your parents. I know they don't look like youth, but they knew about it. So make sure you learn more about it. And guys, I'm loving what you're doing on the page, so keep posting. But for now, I'm going to hand over to John. John, take it away.
Ty, thank you so much. Guys, we're doing that Rice table. Now, I want to take it slowly, but we want to get this right. If you've got questions about this, please post them on the page. After the show, I'll be online and I'll take any of your questions about this particular example. Please make sure that you're getting it right. We'll take it slowly and we'll make sure that we'll get this one sorted. Okay, so we've got our given information. We know the number of moles and we've sorted it all out, got the right units, and we've got a mark already over here because we've written down the Kc expression. So that's a mark in the bag. The next thing is to write down the balanced equation. Now, the ratio of the moles is given from the balanced equation. They've given you the balanced equation in the question, and we know that we've got 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. Now, from the question as well, we know what the initial things were. We know that we had 2 moles of hydrogen and 1,5 moles, so we fill that in. 2 moles of nitrogen, just make sure, of 2 moles of hydrogen. 2 moles of hydrogen and 1,5 moles of nitrogen. So what does that mean? I've got the reactants. If I've only got that stuff and that's injected, have I got any product? No. Remember, these are your reactants. This is your product. And we can say, I've got 0 over there. So put the 0 in. I think it helps. Now we go to the next part of the equation, and it tells us that at the end of the reaction, when it reaches chemical equilibrium, I've got 1 mole. So now I want to explain. Ratio, initial, then it says change. What has changed? I skipped that row, and that's why we say it's rice. Okay, R for ratio, I for initial or start, C for change, and E for equilibrium. And I've put another E because I want equilibrium in moles and then equilibrium in concentration. So I was told I've got 1 of those at the end, at chemical equilibrium. So that's the given information. I've recorded the given information into my table, and there it's sitting like that. Now I've got to do some manipulation. I've got to start doing some working out. Now, here's something that I find very useful. Anything that is produced, anything that is on the other side of this double arrow here, okay? Anything on the other side of the arrow, of the reaction coordinates, I'm going to make this positive. I'm going to say I'm adding to it. When I make something, I'm going to make sure it's plus. What I'm going to do now is I'm going to say, if I started with this and I got to that, so I started with 0 and I'll get to 1. What happened? What was the change? Well, the change is I've got plus 1. So 0 plus 1 gives me 1. These 2 lines I must add together to give me the answer here. So 0 plus 1 gives me 1. Now, here's it's not tricky, but you just need to know it. We want to find out what the change is over here and here. How are we going to work it out? Well, the good news, guys, is I've labeled them in green. I put ratio and change in the same color. And what that's telling me is that whatever answers I get in this line, they must be in the same ratio as that line. So now this becomes a really basic calculation. Now, I know that not all of us do Maths Lit, but the Maths Lit guys are brilliant at ratio. If you're struggling and you do core maths, you might have forgotten about some of the ratio calculations. Go and ask a buddy who does Maths Lit. They'll tell you all about ratio. So, but here's my way of doing ratio. I reckon that I've got 2 parts here, and I've only got 1 part here. I want to get 2 is to 1. I'm saying 2 to 1. What did I do to the 2 to get 1? I divided by 2. Easy? So what must I do to the stuff that I've got over here to get to 1? Look over here. This is the ratio here. This is 1 part. I want it to be in the same ratio. 1 is to 2. So between this one and this one, there must be a ratio. So 1 is to 2. It must be in that ratio. What am I going to do to the 1 to get the equivalent ratio here? I must divide by 2. So what am I going to do? I'm going to say 1 divided by 2 is equal to a half, 0.5. Notice, if I doubled this, I would get 1. If I double that, I get 2. But remember the other thing that I said. I said on this side, I'm going to do a plus. On this side, I'm going to do a minus. So I'm going to make sure that that's minus 0.5. So I've now got the 1. If I found the 1 of the ratio, then it's easy to find the 3 parts. I need this to be a 1:3 ratio. I need this to be a 1:3. So if this is 1 is a half, then what is 3 going to be? 3 times a half? 1.5. I hope you got that. 1.5. We put a minus over there. Now, just double check yourself. Let's multiply this row through by 2. Minus 0.5 by 2 gives us 1. Minus 1.5 by 2 gives us 3. 1 by 2 gives us 2. It's in the same ratio. You can check it. Make sure you got the ratio sorted. Now the next part is easy. Remember what I said over here? We're just going to add these 2 rows. We're going to forget about the ratio line now, and we're just going to do with the initial and the change. We're adding those 2 together. 0 plus 1 gives us 1. Now, what are we going to do when we get 2 and minus 1.5? Oh, guys, that's not difficult. A half. 1.5 minus a half, 1. Those are the moles that we've got. What about our concentration? Well, remember, we said it earlier. Concentration is the number of moles divided by volume, and we've got a volume of a half. So what we must do to each of those, we must divide by a half. Now, here's something that I know that does work on the calculator, and you can put it in, and that's fine if you're comfortable with that. But if you divide by half, it's the same as multiplying by 2. So it's easy. Multiply 1 by 2 gives you 2. Multiply a half by 2 is 1. Multiply 1 by 2 gives you 2. Those are your concentration values. Where are you going to substitute those in? You're going to substitute those in back into this equation over here. You're going to substitute it back into your equilibrium expression so that you can write down your final, just undo that, you can write down your final answer. So I'm going to just do my working over here. You can obviously rewrite this. I just haven't got time to do that, and do the substitutions. So let's make sure we've got it. 2 is the ammonia. So I'm going to substitute into 2. I'm going to put 2 where I see the concentration of ammonia and square it. What was the concentration of hydrogen? Look, under the hydrogen line, all the way down, concentration is 1. So I must put the concentration of hydrogen 1 cubit multiplied by my concentration of nitrogen. The end, my concentration of nitrogen was 2, and I substitute that in. And I don't have to square it or do anything. What do I get? I get 4 over 2, which is going to give me an answer of 2. Remember, KC has no units. It's just that answer. Okay, guys, that's about it. Remember, we're back next week with revision, term 2 revision. But Ty, life science is up next.
Yes, exactly. So guys, make sure you stay tuned. Do not go anywhere, because we've got another exciting session of life science coming up. So guys, make sure you enjoy your June 16th. And guys, for me, I'm going to sign off and say see you next time.